Everybody, I'm Andy Avenow. I'm just going to lead off with a couple of slides and then hand over to my colleague Paul. So we'll just run through the slides. If you have any questions, you can put them in the chat area and we'll address them during the presentation. So everybody, please just mute your microphone so we don't have noise across the presentation. And say if you have any questions, put them in the chat and then we'll look at them as we go through and address them. And as Bruce said, the webinar is recorded, so you will have an opportunity to replay it later. So I'm Andy Avenow. I've been with Crowcon 25 years. I'm head of sales support, which means that I just use my experience in gas detection to support the sales teams. And my colleague here is Paul Basham.
Good morning.
He's also been here about 25 years. And Paul's our principal scientist and works with our research and development team. So we're part of Crowcon. Crowcon was established in 1970 in Oxford, mainly at that time making portable gas monitors. And since then we've grown hugely. We're still in the Oxfordshire area, where we're just down the road a little bit from Oxford now, but we're still based in the same area. And we've got well over 500,000 instruments in the field all around the world, both portable and fixed monitors. And we're leading experts in process and infrastructure safety. So we're into many, many markets. And for many years, we've been in the brewing and winemaking industries, helping to protect workers against gas hazards. And we're always looking to pioneer technology first. And we're talking about a particular innovation in sensing technology during this presentation. Crowcon is part of Halma plc. So Halma is a company that's listed on the UK Stock Exchange, the London Stock Exchange. Halma is basically a company that owns companies. So Halma owns about 48 companies currently, with about 48 autonomous companies. We all work autonomously. We don't all look like each other. We have our own business processes and we're in different markets and spread across different geographies. So Halma has a strategy where it's not dependent on performance in one particular geography or performance in one particular market. It spreads its business across different geographies and markets and operates in 24 countries. Halma is listed on the UK Stock Exchange, FTSE 100 company, and the turnover last year was in the order of £1.8 billion. So Halma provide great financial security to Crowcon, and obviously Crowcon provides profits to Halma. So it's a good working relationship. And Halma's strategy is to grow a safer, cleaner, healthier future for everyone, every day. So Paul's just going to present a few slides on hydrogen generally.
Good morning, everyone. Methane is one of the simplest hydrocarbons, and it's generally burned to give off heat, to heat homes and provide energy to businesses. You can see there the majority of homes and a good percentage of the country's electricity are generated by burning methane. Unfortunately, as heat is given off, methane produces carbon dioxide. It also produces steam, but the carbon dioxide, which comes off as a waste product, is the main contributor to global warming. I'm sure you've seen the effects of global warming in the news. There's a move internationally to decarbonise fuel, and clearly hydrogen is one possible fuel that if you burn hydrogen, it doesn't give off any carbon dioxide because there's no carbon in hydrogen, and so that is a good way forward. All it gives off is the oxide of hydrogen, which is steam. Hydrogen gas thus gives off water vapour as its only product apart from heat, and that has zero global warming potential. Obviously there's already clouds in the air, and so it doesn't really add too much to it. There are different colours of hydrogen. These are obviously not the colours of the gas. These are descriptions of how the hydrogen was produced. If you've got a process, if you've got a clear way of producing hydrogen from renewables by electrolyzing, then we call that green hydrogen, because obviously there's no waste gases of carbon dioxide to release to the environment, because you're using a renewable source of energy. There are other forms of processes by which hydrogen can be produced, of course. One of those, which is used currently to make more hydrogen than green hydrogen, is the steam reformation process, which produces quite a lot of carbon dioxide. Now, if you capture that carbon dioxide with carbon capture and storage, then we call that blue hydrogen. If you don't bother to capture that, then it's quite bad for the environment, because that carbon dioxide is released to the atmosphere, and the steam reformation process is only around 65% efficient anyway, and so you get even more carbon dioxide than you otherwise would given off to the atmosphere, and we call that grey hydrogen. There are some other colours of hydrogen as well. If the electricity you're using in your electrolyzer is derived from nuclear energy, then it's often called pink or red hydrogen. If you're burning lignite to generate the energy which you're then using to electrolyze the water to get the hydrogen, then we call that brown, and if it's coal, then we call that black hydrogen. There have been, over the last decade, a lot of schemes started and policies developed around the world to promote the hydrogen economy, and these are listed on this slide, and you can see that even over the last decade, it starts out with a few tentative basic hydrogen strategies and so on, and it ends up with quite a number. Quite a density of actually commercialised supply chain and groupings of companies and countries making policies that are promoting hydrogen use. You can see from this slide. I'll pick out a few things. There's the high deploy in July 2021. Actually started a little bit before that, in Kiel University, where there were 400 homes that were on a separate loop, and they were given hydrogen from a local electrolyzer that was installed there, and that was a research level deployment. Since then, there's been Northern Gas Networks in the UK built a system near a place called Winlayton near Newcastle, where they fed 670 homes and a church and a school with hydrogen in the methane. That was a blended 20% hydrogen, 80% methane mix, and found that there were no bad consequences of having an amount of hydrogen in the methane mix. There are now going to be sites up at Redcar, Whitby and Ellesmere Port where they're using 100% hydrogen, and in some trial sites of up to 2,000 homes, and those are going to clearly need different different boilers and different other appliances in the homes that run from neat hydrogen rather than having a high percentage or totally methane present. But you can see from that slide the increasing amount of activity globally in the hydrogen economy. When you burn hydrogen, which you do when you get up to 40,000 ppm or 4% of hydrogen in air or above, then it's if you remember back to your school days when you burned hydrogen in a test tube and you hear a pop, that's the same combustion process that's going on here when you burn hydrogen in a controlled way. What you get off is heat energy, and the hydrogen burns in a very rapid way compared with other hydrocarbons like methane. And so if you don't contain it well and control it well, then hydrogen can be quite a dangerous gas to burn. Although it burns when you do get it wrong and there's uncontrolled exothermic reactions, it doesn't burn in quite such a forceful way as the other hydrocarbons that are generally burned, like methane or propane or LPG. And so it doesn't have such an explosive force behind it. However, it does burn very quickly. The rate of burn is very fast for hydrogen, simply because the molecule is so small. And a measure of that is the speed of sound in hydrogen is about 3 to 4 times the speed of sound in methane. And so you can see that that hydrogen is a very mobile molecule, and hence the uncontrolled burning, unless you're really on top of controlling the hydrogen source. Hydrogen is not toxic, but of course it can displace oxygen and air and thereby cause asphyxiation. It's less likely to do so than heavy gases, which collect from the floor up, because it collects from the ceiling downwards, and there's often vents high up and things like that in buildings, and but it is possible to trap enough hydrogen in a room to not only cause a dangerous explosive mixture, but eventually to cause there to be not enough oxygen to breathe. Hydrogen is a dangerous gas, but if it's properly managed, it can be controlled safely.
Okay, we just got a couple of items coming to the chat, which I'm just going to have a look. So one of the questions: what size manufacturing facility is hydrogen suitable for, or is it for more residential industrial areas? I think the intention is that it will be used across industry and domestic applications. Do you want to comment on that, Paul? Yes, its use in those areas that I mentioned earlier has been entirely domestic. However, up in Redcar, there are industrial estates that those will be. Those will have full 100% hydrogen supplied to them. However, the majority of the testing that's been done at the moment is for domestic environments. Now, there are possibilities for using hydrogen on larger scales as the energy source
in energy intensive industries, you're thinking of steel and of some agricultural material manufacture, but so far those aren't prevalent. It's nearly all been for domestic so far.
I think ultimately the tests that are going on that Paul described are in domestic environments, but I think the outcome of those tests will determine whether it's viable for the entire gas network to be converted to hydrogen over time. So I think there is an intention for the domestic gas and the countrywide gas networks to be converted to hydrogen if the tests prove that it's viable. Obviously there are great challenges in doing that. But right now, there are companies, startup companies, who are providing equipment to generate hydrogen locally. So you can have a container, an electrolyzer on your site that will electrolyze water and convert it into oxygen and hydrogen, so you can run local facilities from your local hydrogen generation equipment. We've seen this in mining, certainly in Australia. So there is a big move to run all the vehicles in the mines from hydrogen powered vehicles and generate hydrogen locally at the mine site. So in the interim for industry, it's likely to be hydrogen that's locally generated by electrolyzers, which will be sited at the individual business location. Okay, so we're a gas detection company. So we know obviously hydrogen is a potentially dangerous gas, and the applications for detecting hydrogen are becoming more diverse as people start to use it as a general energy source. So our job is to help customers to detect any risk from hydrogen leakage. And there are a few different sensor technologies that are available now to do it with. Traditionally, our only viable sensor option was the one that you can see on the screen, which is called a pellister, or otherwise known as a catalytic bead. These were developed in the 1950s by the Coal Mining Research Institute for detecting methane in mines, a bit of a more reliable method than using a Davy lamp or a canary. And they operate by heating up a coil of wire in a circuit, and that hot bead, that hot coil of wire is coated in a bead that's catalyzed to react with gas. It burns about 500 degrees Celsius, and when it comes into contact with a flammable substance, the bead will effectively get hotter. It will burn on the gas. Its resistance will increase, which changes the current flow in the circuit, and that change of current flow indicates the gas concentration to the instrument. So it's a very direct method of detecting gas. In fact, the beads are used in pairs. One is catalyzed to react with the gas, one is not catalyzed. The compensator, the second bead, is there to compensate the changes in the properties of the bead due to changes in ambient conditions, in ambient pressure, ambient temperature, etc. Because it's very, very hot, we need to operate it behind a flame arrestor, we call it a sinter, which can present some challenges of getting gas in and out of the sensor, but it will respond to many different gases and vapors. So it will respond to methane, hydrogen, butane, propane in a linear way, so we can calibrate with methane gas and apply correction factors for other gases, but it would only be accurate for methane or the gas that it's been corrected for. If it sees any other type of gas, then it will respond, but the LEL gas concentration reading won't be accurate. So I have an animation here of how the pellister works. So they're normally mounted in a small can within the instrument. At the top of the can is the flame arrestor, the sinter. It's a porous disc of crushed stainless steel particles that allows gas to permeate through, but will not allow a flame to pass back through the other way. So as I said, the beads are used in pairs. You have an active bead and a reference bead. And as the active bead is exposed to gas, so it burns hotter, its resistance increases, offsets the current flow in the Wheatstone bridge circuit, and we're able to determine the percent LEL gas concentration. So it's a very simple, very direct method of detecting gas and very effective, but it does have some drawbacks, which we'll come to in a moment. Because of the drawbacks of the pellister, the limitations, infrared sensing technology was developed during the 80s and 90s, and the first instruments came to market in the 1990s, and it uses an optical method of detecting the presence of hydrocarbon gases. So this technique is only able to detect gas molecules with dissimilar atoms. So things like hydrocarbons have hydrogen and carbon atoms. Carbon dioxide has carbon and oxygen atoms. It's not able to detect elemental gases such as hydrogen or nitrogen. It works by using two sensors that are looking at infrared energy at wavelengths that will be absorbed by hydrocarbon or carbon dioxide gases. For hydrocarbons, absorption happens at a 3.3 micron wavelength. For CO2 measurement, absorption happens at 4.2 micron wavelength. So the very finely tuned infrared sensor can measure a reduction in infrared energy at those specific wavelengths to determine the presence of gas. Just like the pellister, we also need to have a reference wavelength so that you can determine absorption of energy due to gas as opposed to absorption of energy due to contamination on the window or the mirror, or perhaps the infrared source starting to fail. So the system is measuring the difference between the two sensors in the detector. So there's my very simple depiction of gas molecules. Methane molecule is the simplest hydrocarbon. So it has one carbon and 4 hydrogen atoms within the molecule. I've put ethane there for comparison, which is C2H6, slightly more complex hydrocarbon. So as you can see, there are more atomic bonds within the molecule. And if these gas molecules are exposed to infrared energy at around 3.3 microns, then those atomic bonds resonate within the molecule, and that resonance absorbs the infrared energy and basically reduces the amount of infrared energy that's seen at the sensor. And it's that reduction of energy that the detector relies on to detect the gas. I've also shown a hydrogen molecule, which is H2. Because you don't have dissimilar atoms, there is no resonance within the molecule, and therefore you can't detect hydrogen using infrared technology. So again, a very simple animation just showing how infrared sensing works. So most instruments, the sensors and the infrared source are within a small can. On many detectors, the infrared source is a simple filament lamp. On this model, it's actually infrared LED emitters that are emitting infrared energy at the two wavelengths, the 3.3 micron sensing wavelength and the 3 micron compensation wavelength, which is there to determine energy absorption due to contamination on optical elements in the sensor. So the system is constantly monitoring the two different wavelengths and comparing the output signal of the sensor at the two different wavelengths. So you can see the infrared energy is reflected on a mirror. And as gas enters the sensor, the 3.3 micron energy will be absorbed. So the sensor measures the difference in output from the two sensors, and it can determine gas presence as opposed to energy reduction due to contamination, and give us a % LEL gas reading. So comparing the two sensor technologies, the key problem with pellisters, and it's a very real problem, is poisoning. So the pellister bead is relying on physically coming into contact with the gas in order to detect it. If the pellister is exposed to substances like silicon, which is a very large molecule, the silicon will coat the pellister bead, will fill in the pores on the pellister bead, and effectively form a coating on the bead which stops it physically coming into contact with the gas. So it then just doesn't respond to the gas. And this is not just silicon, it also is leaded compounds, chlorinated compounds, fluorinated compounds. There's lots of different compounds that will have the same effect on the pellister. It remains operational electrically, so current still passes through the bead. So the instrument still thinks the pellister is working fine. You don't get a fault on the instrument, it just doesn't respond to gas. So this is what we call in our industry an unsafe failure, which is very undesirable. You don't know that your sensor is not responsive. So that's the number one problem with pellisters, and silicons are present everywhere in our, all around us. Hand creams, polishes, waxes, greases, they all contain silicons, and any exposure to the pellister silicon will begin to poison the pellister. So you can only tell if a pellister is poisoned by putting test gas on it. That's the only way to tell. So pellisters do need very frequent testing with test gas to ensure that they're still operational. Infrared sensors can't be poisoned, so that's not an issue, and infrared sensors do fail safe. So if the lamp fails or a sensor fails, you do get a fault on the instrument. Pellisters also require oxygen to work, so they can't be used in oxygen-reduced atmospheres, whereas infrared sensors don't need the oxygen to work, but pellisters detect hydrogen and infrared sensors don't. So for the purpose of this presentation, infrared sensors are pretty useless because it will detect methane, but it won't detect hydrogen. Pellisters also are designed to work up to 100% LEL. Ever exposed to gas concentrations above, then there is a risk that the pellister will actually burn out and will need replacing, whereas infrared sensors won't be harmed by exposure to high gas concentrations. And being a thermal device, a pellister has a relatively limited life, 3 to 5 years in most applications, but then the pellister has to be replaced, whereas an infrared detector will last 10, 15 years plus. And a pellister is a fairly low cost device, whereas an infrared detector, being more sophisticated, is a slightly more expensive device. So just before I go into new sensing technology, I'm just going to check the chat. There's one more question showing in the chat. There's one for Paul.
We're mentioning blue hydrogen where carbon dioxide is stored in the ground. Is there any way this CO2 can be reused and thus help ameliorate the CO2 shortages we're encountering? Theoretically you could, but no one does in practice. The places that use steam reformation, there's a big place in Australia where steam reformation is used at the moment. There are two things that happen where either the CO2 is just let go into the atmosphere, but for grey hydrogen, but for blue hydrogen, what they're doing is capturing the carbon dioxide and storing it in the ground. In theory, you could use it in the manufacture of fertilizers, but no one has, and I don't know why.
No, I agree with Paul. In theory, it's some of the market that could be tapped into capturing carbon dioxide and then using it in the drinks industry. Absolutely, in theory, it's possible, but I'm not aware of anybody doing it in a commercial way. Okay, we'll just carry on with the presentation. So I've outlined the two traditional sensing technologies for flammable gases that have been relied upon for decades. So there's still the two main sensing technologies. However, there is a new sensor that's become available called the MPS sensor, the molecular property spectrometer, which is a real game changer in our industry and is absolutely ideal and has come just at the right time to solve the problem of detecting hydrogen in a dependable way. So the MPS sensor works on the principle that the normal composition of air is fairly defined and stable. So you see a pie chart there. The composition of the air that we're breathing is mainly nitrogen, about 78%. It's about 20.9% oxygen. There's about 400 parts per million carbon dioxide. And then there are some other gases making up the remainder, the most notable of which is argon at just under 1%. So the sensor takes that air mix as stable as a norm, and it's measuring changes in the thermodynamic properties of the air mixture which it's exposed to. And the thermodynamics will change as the mixture of air changes, and that will include the introduction of things like hydrogen and other flammable gases into the air mix. So it's using that air composition as a baseline for its measurement, and any changes are compared to data that's stored in the sensor. So that's what the sensor looks like. It has a tiny transducer. It's a MEMS microelectromechanical system transducer, very, very low mass transducer that can be heated up and cooled down very, very quickly. It also includes a joule heater, which is able to measure the amount of energy that's taken to heat the MEMS sensor up, and then there's a resistance thermometer. They're mounted on a PCB within a small sensor housing, and there is a gauze that enables air to enter the sensing chamber. And as I said before, it's constantly measuring the thermodynamic properties of the air to which it's exposed. So air can diffuse into the sensor through the gauze and comes into contact with the MEMS sensor module, and then there is a joule heater that's rapidly heating up the MEMS sensor plate. It heats out to about 900 degrees Celsius every 2 seconds, so it's able to heat up and cool down again to 900 degrees Celsius from ambient every 2 seconds. And the joule thermometer is measuring the amount of energy that's taken to heat that hot plate back up to 900 degrees Celsius. And that energy will change depending on the thermodynamic properties of air, because different gases will conduct heat away from the plate at different rates, depending on their own thermodynamics. It also has to factor in real-time environmental conditions, because of course that will also influence the amount of energy needed to heat the hot plate. So there is a temperature sensor, a pressure sensor, and a humidity sensor also on that top PCB that's permanently exposed to the environment. So the sensor system is taking measurements from the hot plate, but it's also taking measurements from those other 3 sensors and factoring them all into the measurement algorithm. And it's just constantly heating up that sensor plate and measuring the amount of energy required to heat it back up to 900 degrees Celsius. And then it compares its results to an algorithm stored within the microprocessor, and from the results it's able to classify the types of gas it's seeing according to molecular weights. So it's able to classify whether there's hydrogen present or slightly heavier or longer chain hydrocarbons in the mix. So there are lots of benefits of the MPS sensor over both the Pellister and the infrared gas detector. The first being the true LEL accuracy. So I've said before that a Pellister will detect lots of different gases and vapors, but it will only be accurate for the gas that it's calibrated with. It will detect, if it is calibrated with methane, it will detect hydrogen, but it will give you a slightly incorrect reading. An infrared sensor will also detect other gases and vapors. So an infrared sensor calibrated for methane will detect propane or butane or pentane, but it will be wildly inaccurate. It will massively over-respond. So the reading you get will be a much, much higher concentration than is actually present. And as we've discussed before, the infrared sensor can't detect hydrogen at all. So we're left with the Pellister conventionally, but the problem is Pellisters get poisoned, and they really do. So you have to gas test them all the time to be sure that they remain operational. And as I said, the Pellister is only accurate for the gas that it's calibrated for, but you can calibrate it for hydrogen. It will be accurate for hydrogen if that's your primary risk in your environment. The Pellister can be also has a short life, so if it sees a high concentration of gas, it's likely to burn out. And as I say, it does need regular calibration. Pellisters can also give false readings if there's big swings in pressure in the environment or humidity or temperature. The Pellisters generally work over quite a wide temperature range, up to about 50 degrees Celsius. However, the MPS sensor is able to work up to 70 degrees Celsius, and the MPS sensor will last more than 10 years without calibration for at least 5 years. So the MPS sensor does not need calibration. Its calibration is guaranteed for 5 years, which means operationally it's a huge cost saving not having to use test gas to calibrate your sensor. Pellisters require calibration every 6 months at the absolute minimum. So this short animation shows test data which proves that the MPS sensor outperforms the Pellister and the infrared gas detector in a scenario where we have exposure to different gas concentrations. So here we have test data with methane applied to all three different technologies of sensor that have been calibrated with methane. So you can see they all respond accurately to methane. The MPS, NDIR is the infrared sensor, and the Pellister. If that same sensor is then exposed to butane, you can see that the infrared sensor gives a huge overread. The Pellister is a bit inaccurate, whereas the MPS sensor remains accurate. And if hydrogen is then exposed to the sensor, again, the MPS remains accurate, the Pellister underreads, and the infrared detector doesn't measure hydrogen at all. And this is exposure to a mix of gases, so 50% LEL of methane, 20% LEL of hydrogen, and 10% LEL of butane. So if you have a mixture of gases, your response from the IR sensor and the Pellister are relatively low, whereas the MPS sensor still reports over a second level alarm at 40% LEL. And that's because it's measuring those different gases accurately. So the MPS sensor isn't vulnerable to poisoning, it gives true LEL accuracy, is calibration guaranteed for 5 years, and it detects hydrogen. And just to demonstrate the risk of poisoning, again we have a short video here. Oh, you can't hear Rachel. Sorry Rachel, we can't hear you. I'll talk through what's happening on this video. So we're going to demonstrate the poison resistance of the MPS sensor compared to a Pellister sensor. They're both calibrated for methane, although as I've already said, the MPS sensor will also respond very accurately to hydrogen gas. So we have a chamber that has a Pellister sensor and an MPS sensor inside, and we have a balloon that's filled with methane. And this test is to demonstrate the vulnerability of Pellisters to poisoning from a silicon product, and to demonstrate the MPS sensor is not poisoned by the same compound. Sorry, Rachel talks more than I do. We'll get to the test. So in that bottle is some vehicle detailing spray, sort of stuff that my son sprays on his car to make it look nice and shiny, and it contains a high level of silicon. And there's a towel there that the silicon spray will be sprayed onto. So the balloon is burst, and so that chamber is now filling up with methane at about 50% LEL. And you can see the response from the two sensors. This is time is sped up a little bit. But you can see there's a response from both sensors to the gas in the chamber. Albeit the Pellister response is lower than the MPS sensor response. So now some of that silicon spray has been squirted onto the towel that's hanging at the top there. There's a fan in the chamber just moving around the gas in the chamber. And you can see pretty quickly that the red line from the Pellister sensor starts to dive downwards. And that's because the Pellister is being poisoned and becoming less responsive to the gas. So you can see it's becoming less and less responsive. And after 1.5 hours, the MPS sensor reading is 42% LEL, and that's because the chamber is not perfectly sealed. Some of the gas is leaking out, but you can see the Pellister is reading 0. It's totally poisoned, completely inactivated by the silicon. And that poisoning of the Pellister is permanent. You cannot recover that Pellister once it's been exposed to silicon. So you can see on the follow-on test, now more methane is introduced to the chamber, the MPS sensor responds, the Pellister doesn't respond at all. And that's a dangerous situation because the pellister remains electrically operational. The instrument thinks the pellister is fine. Current's still flowing through it, it just doesn't respond to gas. So the MPS sensor is developed by Nevada Nano, and we've worked with them. It was developed for other application, and Crowcon has worked with Nevada Nano to put it into gas detection instruments. Okay, before I run through the test data, we've got another question in the chat, which we'll just have a look at. Okay, is there a standard life of a pellister, and is there a large difference between the price between pellister and MPS? So the life of a pellister absolutely depends on the environment it's exposed to during its life. So if you are in a very clean environment where there is no silicon, no lead, no sulfur compounds, it doesn't get exposed to much gas, then a pellister might last 5 to 10 years. It can, they can last a long time. However, in real life, most pellisters require replacing at least every 5 years, and in industrial applications, possibly down to 3 years. It all depends. The pellister's life will be shortened by exposure to silicon or leaded compounds. And as I said, be careful with silicon because it's present in the mastic around your windows. It's present in the polish that you polish your floors with. It's present in hand creams. It's present in shampoos. It's present everywhere. And also gas exposure. So the more times a pellister is exposed to gas, the more its life will be consumed. So we generally say 3 to 5 years, and in fixed applications that's probably about true. In portable applications, it can also depend on, if you use your portable instrument on site during the day and the site is nice and clean, that's great. But then if you put your portable instrument in the back of your van where you've got some of that polishing compound, your portable instrument can be poisoned overnight just by laying in the van with some silicon. So it completely depends on the application, and the key point is you have to keep gas testing your pellister to be sure it works. That's absolutely paramount. With the MPS sensor, it can't be poisoned, so that need to keep testing it is greatly reduced. Okay, so we have some data that's been derived in our laboratory at Crowcon. Here on the left, you can see 5 years worth of data to demonstrate that the MPS sensor doesn't need routine calibration. You've got data points across a 5-year period there where gas has been applied without recalibration of the sensor, and the signal still remains accurate and consistent. So it really doesn't need calibration. And this is our test at Crowcon for the exposure to different gases. So with a standard methane calibration on the MPS sensor across 6 different detectors, you can see that they all read very consistently. The output from all 6 detectors are very tightly packed together for methane. And if the same sensors without recalibration are then exposed to butane, they're still very accurate on butane. The dotted lines above and below the response line are the limits of accuracy that are allowable in the European performance standards. So ethane, ethylene's a bit more challenging, hydrogen, LPG, pentane, propane. So you can see across the spread of those 6 detectors, across the spread of all of those gases, they still remain very accurate just with that standard methane calibration. And in environmental tests, you can see that we've exposed sensors to gas at minus 40 degrees Celsius, minus 20, 0, plus 20 degrees Celsius, and plus 40 degrees Celsius. And the response remains consistent and accurate. And that's because of the temperature compensation in the sensor. And again, changing humidity from 10% to 50% to 90% relative humidity results in consistent readings from the sensor as well. So environmental effects changes are very accurately negated in the algorithm of the sensor. So we've worked with the sensor, the people who developed the sensor for different applications, and we've worked with them closely to make it usable in gas detection products, safety products, and we've put it into our fixed and portable monitors. So we put it into XGuard Bright, which is our fixed point gas detector, which can be permanently installed on site, Incidentally, we also have a carbon dioxide sensor available in the XGuard Bright for the brewing market. We put it in our single Gasman portable monitor, and we have the MPS sensor also available in our T4X 4-gas personal monitor. So the XGuard Bright is a fixed point gas detector, is permanently installed on site. It has a display so you can see the gas concentration locally. It has analog or RS485 digital signals for communicating with the control system. It has relays on board which can be used to trigger a sounder and a beacon locally. And as I say, it's available with the MPS sensor for hydrogen detection, but it's also available with a carbon dioxide sensor. And we do have some of these instruments in stainless steel enclosures in breweries across the UK. Stainless steel is important because in a brewing environment, the carbon dioxide laden environment is quite corrosive, so we wouldn't recommend aluminium. That's why we have the 316 stainless steel version available. And then quite often our XGuard Bright detectors are connected to a control panel such as Gas Master. So the Gas Master would be outside of the area where the gas might be, and the Gas Master does the job of displaying the gas concentrations from up to 4 gas detectors. It has a loud sounder and a very bright beacon built into it, so if gas is detected above an alarm threshold, then the user is alerted very clearly. And of course you can see the gas concentrations on the display of up to 4 gas detectors. And then it has relays in there for triggering loud sounders and beacons, Modbus communications for sending information to other plant-wide building management systems or DCS systems. And being a safe system, it has battery backup as standard, so if the mains fails, the system keeps working seamlessly. And it has a high ingress protection, IP65, so if there is washdown operations or water being sprayed around, then it has a good level of protection against water ingress. And we also have the MPS sensor available in a couple of portable monitors. The Gasman is a single gas monitor, so you could just have just the MPS sensor for protecting workers against combustible hydrogen risk. We also have a CO2 sensor available in our Gasman monitor, and that's generally used in the brewing industry for people walking into the brewing and fermenting areas. It's also used by delivery drivers who may be delivering wine and beers to pubs and bars where there is a risk of CO2 sensors leaking in perhaps a cellar under a pub in a confined space to protect the delivery driver from CO2 exposure during his working day. And then where there is multiple gas hazards, then we can have the MPS sensor in the T4X instrument, and you can also have, for example, an oxygen sensor in addition to the MPS sensor for protecting workers against the risk of oxygen depletion due to a buildup of CO2 or perhaps nitrogen leakage from nitrogen cylinders in pub cellars. So there's lots of more information on the MPS sensor and other technologies on our Crowcon website, www.crowcon.com. You can find blogs, white papers, solutions, data sheets, case studies, and obviously product information. And you can contact us for more information using these contact information details. All right, that's it for the presentation. Does anybody have any other questions? There are none in the chat at the moment, so please type them in now if you have any questions.
Hi Andy, we'll be sending a feedback form out, and on there will be the opportunity for them to ask any other questions, and those that are here and those that will be watching the video later on, you can see there's an email address there and a phone number that you can contact. So thank you for supporting the event, and thank you to Andy and Paul for a really informative presentation. I'll let you get on with your day. Goodbye.
Thanks everyone.